Good morning, everybody. How y'all doing? So today we are going to start with part 2 of this chapter. This is where we're going to start digging into chemical equations. We're going to look at the different pieces and parts of a chemical equation. What do they mean? What are they trying to tell us? What's really important to know, like wrap inside your head, these are recipes. It's about the same as a chocolate chip cookie recipe. You can write a chocolate chip cookie recipe in the format of a chemical equation and it would work perfectly, except for like the timing and stuff. But anyway, like that's what it is. It's like a chemist's recipe. We're gonna dig into them so we can get all the information that we need out of them. And then for part 3 of the chapter, we're gonna take what we learned in the first part, like with all that stuff about like gram formula, mass, percent composition, how much stuff or how much of an element you have in the sample, all that stuff that we did last time. We're going to combine it with the information that we're learning about chemical equations. Then we're going that way we can learn and see what we do actually with chemical equations and chemistry and science for real actually in the lab. So we're going to tie both of these parts together at the end of the chapter, but for right now, let's dig into some chemical equations. All right, so chemical equations, what are they? It's a recipe, guys. Basically it's like a chemical recipe. And they describe chemical reactions. They kind of tell us what's going on, what's being made, what's being used up, how much is being made, how much is being used up, what are the proper ratios of everything in a chemical reaction. So yeah, we touched on what is a chemical reaction. We kind of touched on this a little bit in chapter 1 when we learned about chemical change. So a chemical reaction is basically a change that results in a new substance. And we kind of went, like, you guys already know how this works from last time, right? Like where you take firewood and it turns into carbon dioxide and water vapor, right? That's something new. Where iron turns into rusts, digestion. This is where like your cheeseburger turns into, well, it's not a cheeseburger anymore. That is for gosh darn sure. You know what I'm saying? So like really, really different substances. Yeah. Also, baking, cooking, dude. Cooking is a chemical change. We definitely cause a chemical change when we cook. Look at a raw egg versus a cooked egg, dude. The properties are drastically different, right? Right. So when we say it is a chemical reaction or a chemical change, totally different substances. What you start with must be completely different from what you end with. However, the pieces and parts are the same. Right? This is something that kind of throws people off, where like you might start with something with carbon and oxygen, and you're going to end with something with carbon and oxygen. But if the configuration is different, then it is a totally different substance. The same atoms and elements, just rearranged into something completely different. So how do we tell? How do we tell when we put two things together if there is a chemical reaction? So we're going to go over this. We're going to go over, like, I think there's 5 indicators. I hope I'm not wrong. I guess we'll find out. But these are just indicators, guys. These are not, it's not like a guarantee, like, oh, if it's exothermic, guaranteed chemical reaction. Because not always. There are some processes that are exothermic that are not a chemical reaction. So these are indicators. Hints. Guarantees? Nah. All right. So numero uno, the first indicator is any kind of change in temperature, right? Anytime you put two things together in a beaker and the temperature changes, there might be something going on there. All right, so, and we basically have two directions. Temperature can go up or temperature can go down. And what that means is that energy or heat energy, like this guy right now, the heat miser, heat is either leaving the chemical reaction, it is either exiting the chemical reaction, or heat energy is being absorbed from the surroundings into the chemical reaction. Two options, in or out, that's it. So we have words. Exothermic means it's giving off heat, right? Because exit means exothermic. If Mr. Heat Miser is leaving, if it goes out of the chemical reaction, it is exiting, and that is exothermic. Got it? Now the other one is endothermic, right? Endothermic means heat is entering the chemical reaction. Just like if like Mr. Heat Miser, if he goes into or if he enters the chemical reaction. It is endothermic. Do you see these prefixes here? It's almost like sometimes the English language makes sense. Not often, rarely, but there it is. Exothermic is when heat exits the system that you're looking at, and endothermic is when heat enters the system you're looking at. Two good examples of this are like exothermic. Those are those little heat pads, right? It's like during winter, right? Like little hand warmers. You open them up from the package, you shake them up, and then you put them in your pocket, and they get so toasty warm. That's a chemical reaction that is exothermic. Heat is being given off. Another good example for endothermic are those cold packs that your coach might have if you're playing soccer or football or whatever. Twist your ankle, then there's like a bag, and you break the bag inside of it and shake it up real good, and it gets cold. I mean, not freezing cold, but it gets colder. That's endothermic, where the process that's happening inside that bag is absorbing heat energy from the surroundings. So you put it up against your ankle, and it's absorbing heat out of your ankle in an effort to cut down the swelling. Right, just rice. All right, that's one. Change in temperature is one indicator. Another indicator is a release of gas, and that'll look like bubbles. I mean, really, gas. If you take two liquids and you pour them together and they start getting bubbly, gas is a whole new form of substance. So it's probably a brand new substance, right? I mean, right? Like baking soda and vinegar. Baking soda is a hard, solid. It's like a granular powder, right? And vinegar is a liquid, and when you put them together, you get bubbles. Dude, bubbles are neither a liquid and they're not a solid granular, so it's definitely something new. Does it guarantee? Nope. There are some processes that give off gas that it is not a chemical reaction, but it's a pretty good indicator. The other one is what we call precipitate formation. Precipitate. If you don't know what that is, you should look right down there. A precipitate is a solid that forms out of solution or falls out of solution. It's just like precipitation is when water falls out of the atmosphere. In chemistry, a precipitate is a solid that kind of falls out of solution, and right down here, these guys right here, right there and there, we have a couple of precipitates. Now this one, ooh, that's a little too far down, guys. Don't want that. This one right here, this here yellow guy, that's actually a lead precipitate. If we take two liquids and we pour them together, and the right things dissolved in it, you'll get this, like, see how it's kind of globby and cloudy? It's because like they form one molecule at a time, so it's kind of cloudy. And this one over here, this is a calcium precipitate. So it's kind of white, just like your bones. And it is a precipitate, right? So this stuff right here and this stuff right here, the yellow and the white stuff, they are precipitates because they don't dissolve in water. So like the two liquids had compounds that could dissolve, but when you put them together, they form a compound that cannot dissolve. And as soon as that they bump into each other, they form a solid, and they eventually just float down to the bottom. You guys follow me? So a precipitate is when a solid forms from mixing two liquids together. The two liquids have stuff dissolved in them, so it's not like two pure substances in a solid. Maybe it is. Man, I don't know. Who cares? You make a solid from two liquids, it's different. So it's probably a chemical reaction. Good? Good. All right, next one. Changing color. Not always, but quite often, if you start with something that's red and it ends up brown, it is not the same thing. And same thing with odor. If something starts out smelling like roses, and it ends up smelling like compost, it's no longer a rose. Right? Now again, changing color, this is not a guarantee that it is a chemical change, and same with change in odor. It is not a guarantee, but it's a very strong indicator that something new has been created. So if you have something like change in color, odor, and bubble formation, and it's getting hot, man, that's probably some kind of chemical reaction. You know what I mean? So these are indicators, things that we can look for that clue us into, hey, something is happening here that may very well mean that we have a chemical reaction happening. Guarantee? Nope. Nope. Not a guarantee, but a pretty good indicator. Oh, I almost forgot. Look at me. Look at me being all nice to myself. Oh, man. Past Micah is really happy with present Micah. So look at that. Look at table F. Look at table F. So this thing right here, that lead precipitate, the only way that we're going to know if it's going to be a solid in solution is if it doesn't dissolve. And table F on our reference tables helps us do that. We will talk about that like when we're actually looking at each other and maybe a little bit later. But I want you to dial into table F because that's something that we're going to need to pay attention to moving forward. Got it? Awesome. So that's it for that's not it, but this is what we've got. We've got a chemical reaction is something that results in a whole new substance. And how do you tell if there's a chemical reaction? We got change in temperature, formation of a gas, formation of a precipitate, change in color, change in odor. That's how we can tell that a chemical change is happening. And we capture that chemical change and we write the chemical change in a chemical equation. So here's how the chemical equation is written out. This is like the general format. We have reactants and we have products. Now, reactants are like ingredients, right? These are the things that go into the into the reaction, and then the product is what you make. It's what comes out, right? So on this side, for reactants, if we're making chocolate chip cookies, it'd be eggs, milk, flour, butter, chocolate chip cookies, a little bit of baking soda. Don't forget sugar. And then we would have a little symbol right here, a little triangle that says you have to heat it up. Then over here, we'd have like 32 cookies, 24 cookies. I don't know, however many cookies you make, right? Yeah, you guys dig how that works? The big difference between like a recipe and like a chemical reaction is that a chemical reaction, we use chemical formulas because they're chemicals. They're not eggs. And that would be silly to like do that. Okay, also, in a chemical reaction, we have chemicals, right? And the chemicals can often show up in different forms, right? We can have something that shows up as a solid. So this S is a solid, L is for liquid, G is for gas, but AQ, this is a new one for you guys. This means dissolved in water. And man, that's actually really important to lock into because most of the really interesting chemistry happens in dissolved water. Like, us. Almost the entire chemistry of the human body happens in aqueous format, in an aqueous solution, because we are basically walking bags of aqueous chemical reactions because we are like made mostly of water. It's because you can do a lot of really interesting chemistry once you dissolve stuff. So it'll look kind of like this, like, I don't know, let's do copper chloride, right? Copper 2 chloride. What is like, it can show up in a lot of different ways. So we use a little subscript like this. There. That means copper chloride solid. So it's going to be like little granule crystals, right? However, we could also go like this and say, typically it's like a cursive L like that. L for liquid. And that means that it is liquid or like melted. So that means not in water. L means liquid, like it's been heated up to the point where it's going to actually melt. And then if we do something like this, that means that we have boiled it. It is so hot, it is now a vapor. It is really, really hot, probably. So that's the difference between solid, liquid, and gas. Liquid means that it is melted. Got it? And then the last one, this thing that I really want us to really dial into is aqueous. That means it's been dissolved in water. And that is actually like an important one for people to lock inside your brain. This means dissolved in water. Because when things dissolve in water, they break, the ions will break apart. So you're not left with CuCl2 in one little block. What you have is copper ion plus 2 chlorine ions. Right? So this means that's what you have actually in the beaker. Okay? So S is solid, L is liquid, G is gas, AQ, aqueous. Got it? Great. Okay, moving on for some really random weird things. This little triangle means heat. I always think of it looks a little bit like a campfire. It's not really why. I don't know why they use triangle for heat, but there it is. ELEC for electricity, because there are chemical reactions that produce electricity. If you remember back up there, there was a picture of some batteries for like an example of a chemical reaction. And you betcha a battery is a chemical reaction. And we're going to spend a whole chapter looking at some crazy chemistry. And also, an up arrow or like or next to a line like that, this means light. Like glow sticks. It's a chemical reaction that gives off light. Dig? Dug? Here's an example. 2 examples actually. This is what chemical equations look like. Reactant, product. Carbon, this is a solid. Oxygen, this is a gas. And then what it does is it burns and creates carbon dioxide, which is gas. That's what happens when you burn charcoal when you're making a barbecue, right? This one is where we start with sodium nitrate and sodium chloride, and we end up with silver nitrate. I'm sorry, and then we end with sodium nitrate. But look, you see this here? That's important because look, here we have aqueous and aqueous. That means that they're dissolved in water, and then all of a sudden over here we have a solid. That is a precipitate. That is a precipitate. Do you guys see that? How we're starting out over here with like all dissolved in water, but over here we got something that's solid. Precipitate. That's a solid forming from like 2 liquids. Now the different forms of chemical equations, it's kind of right in the titles. A word equation, it describes an equation using words, right? So like this word equation is iron plus chlorine yields iron 3 chloride. Solid. Got it? We just use the names. The skeleton equation, now this is something you need to work, like, it's not as clear. This is where it's just reactants and just products. It is not balanced at all. Look, see, we have 2 chlorines here and 3 over here. You can't magically pull chlorine out of space. It doesn't quite happen that way. So a skeleton equation just lists out the chemical formulas of your reactant products, and that's it, nothing else. Got it? It's not balanced, which is something that we will need to be practicing, because you can't magically make stuff appear and disappear. Harry Potter's not real. Super duper unfortunate. The next one is ionic equations. Now this is where we take our reactants and our products and we break them apart into their ions, because if it's aqueous, that's what's happening inside. It's like, if it's aqueous, it's dissolved and all the ions have broken apart and they're just floating around, all mixed up, swirling around inside that beaker, and it gives us just a better idea of what is actually inside the beaker. So it kind of works like this, right? So we're starting out with NaOH. Let me get a good one here. How about we use that? So we just take the sodium and we write the sodium ion. We take the hydroxide, we write the hydroxide ion, but look, there's 2. So there's 2 sodiums, there's 2 hydroxides. We take 1 calcium. There are 2 chlorine ions. Y'all see that? Now for the products, we have 1 sodium ion. We have, 2 sodium ions. We have 2 chlorines, and then we have 1 calcium hydroxide. You dig? And then we have these weird things. A spectator ion. Well, just like a spectator at a sporting event, what do spectators do? They're the ones that they're not actually doing the sport. Like, they're there watching, right? So if you look over here, we've got sodium plus 1 on the left, and we've got sodium plus 1 on the right. Nothing happened to it. Spectator ion. We also, so OH, nope, that's in a compound. Calcium, nope, that's in a compound. Ooh, I see chlorine right here. Chlorine with a -1. And over here, chlorine with a -1. Those are spectator ions. They are ions that did not partake in the chemical reaction. They started out one way, they ended the exact same way. No change in them. So you can see that the OH, the hydroxide, and the calcium, they changed. They went from ions to a compound. So they changed. They are part of the chemical reaction. But the ionic, or the ion equation, right? The ionic equation helps us look at and see each and every individual participant that's happening inside the beaker. There's that. All right. The next one is particle diagrams. And for these, we use dots to represent atoms. And the reason why we do that is because everybody's different. For some people, it's a lot easier to represent atoms as dots instead of like these symbols with letters. it's just easier for the eyes to see and like to tell that things are being balanced, right? So here is our chemical equation, right? Iron plus chlorine yields iron chloride, and it helps us visualize, right? And now this here is our balanced chemical equation, right? We need 2 irons, 3 chlorine molecules, and we will yield or make 2 iron chlorides. And you can see that there are 1, 2 irons here, we have 1, 2 irons there, and we have, for the chlorines, we have 1, 2, 3, 4, 5, 6 chlorine atoms, and 1, 2, 3, 4, 5, 6 chlorine atoms, starting and finishing with the same amount. So sometimes the particle diagrams just help us like count easier. It just sometimes helps people count better. All right, that's it. We're all done. The 2 things that I need to have us done like about the chemical equations is chemical change versus physical change and understanding chemical reactions. I hope you guys have an awesome day. I know I'm going to. And yeah.